Okay, so we're graphing energy as a function of time. We're first going to do potential energy. It's as a function of mgh, which you could substitute as mgy. And regardless of what's going on, so this is a complicated function, we're actually starting here, throwing process in at the highest point. So it doesn't matter because as a function of position, not as time, it's just a straight line based off of this equation. Step 2. We're going to find the points where your kinetic energy is equal to 0. And we're going to mark those as such. So kinetic energy is going to be equal to 0 at the beginning where you're throwing it, and then at the highest point, kinetic energy is equal to 0. Okay? So what that enables us to conclude is where mechanical energy is at those points, at those locations. So mechanical energy starts at 0 here, because 0 of potential plus 0 of kinetic gives you 0 of that. This, you have 0 kinetic plus some amount of potential energy, so mechanical energy is that amount there. Good with that? Okay. Step 3 is determine when mechanical energy is conserved. So during this process, when we're throwing the ball up, so starting here, going to there, when is mechanical energy conserved? Okay, so at some point you let go. We'll just say that point is, we'll just say this point is here, is the release location. Okay with that? Okay. After the release, mechanical energy is conserved. So up until this point, so here, mechanical energy is conserved. All right with that? Okay. If it's not equal, when it's not conserved, it changes. And during this process here, is mechanical energy during the throwing part being gained or lost? Again, it has to start at 0 and has to go to here. Okay, we're just going to assume it's going to be straight. We can't really, that's hard to, I'll come back to that. But you're gaining mechanical energy, okay? Good with that? And then the last thing is kinetic energy. Do not try to do kinetic energy until you've got your potential energy and mechanical energy kind of on lockdown. Because when you're trying to evaluate kinetic energy, it's as a function of speed, and then you're trying to figure out, okay, how fast is it going? I don't know. It's really hard to tell. But if you work backwards and say, okay, mechanical energy is equal to the difference of kinetic energy is the difference of mechanical energy minus potential energy, then things start working out okay. So we'll start here while it's conserved. So the blue, kind of like doing the bar chart here, the blue plus the green has to stack up to the red. Does that make sense? So kinetic energy is going to be somewhere here. Okay? And I'll just kind of like take another point just to kind of show. So the blue at this location is this much potential energy. That plus the green is gonna give you the red height. And that's gonna be like, that, yes, does that make sense? Okay, so this is gonna end up doing that. Okay, there. And then, so it started at 0, ended at 0, so like during this part, we're just gonna assume that it's, because this is straight, this is also gonna be straight. So that's your kinetic energy as a function of position. See how we did not even touch speed other than when speed was 0. Okay? How are we doing there? Okay. So let's consider this. The slope of, we'll start easy. The slope of potential energy is going to give you what? Tell your neighbor, the slope of potential energy as a function of position is going to give you what? So the slope, so that should be, say dy. We're going to say the slope is going to be du over dy is equal to the conservative force. Sorry, negative slope is equal to conservative force. So the slope of this line is going to be what? Gravity. I use green. Alright, so the slope of this is going to be equal to the force of gravity. So this is going to be equal to the force of gravity. It's a positive slope, so it's going to be negative, meaning the force is going down. Good with that? Okay. The slope of mechanical energy is equal to what? In this scenario specifically, think about it. Have a conversation.
It's going to be a slope, so it's instantaneous.
That's going to be equal to applied force from your hand. Because that's the only non-exertive force we have doing the work. You okay with that? And when it's released, there is no change in mechanical energy. The slope is 0. There is no force, non-exertive force. And so your kinetic energy is going to give you what? It's going to give you your net force. Doesn't matter, conservative or non-conservative. Here, that's going to give you the sum of your applied force. If you did a free body diagram, your applied force while it's being thrown minus your minus your force of gravity, accelerating upward as you throw it, that's gonna give you your net force of those two. And then afterwards, that should be just, the slope should just be the force of gravity. See how much you can pull out of a graph? Be ready to milk a graph, like what else? Like what can I glean from this? Okay? Good? So, how'd you find acceleration as a function of position? Which is not a normal request. Does that make sense?
Yeah.
Have a conversation.
You have your first yeah, they divide out gravity to get the mass. And then you times, so then you divide the mass first by the mass, to get your acceleration. Or the slope of the kinetic energy. That makes sense? Yeah.
If you're given mass, you just have the derivative of kinetic energy. Because that would give you. I never
Yeah.
did.
If you're given mass. If you're given mass, then it's net force divided by mass, but if you're not, by gravity. The mass.
You have to make sure.
You also know that after a certain
Okay.
position.
Is everybody good? You're gonna graph force as a function of position. So you're gonna have a positive slope here, into this, then a negative slope here. And then all you do is you take that and divide that by the mass, which is a scalar quantity. You're gonna get the same shape, just different values. How are we doing that? Is that what you came up with?
Yeah.
Okay, so all this is in the realm of possibilities. Okay? Good? So that's how to bake a energy versus position graph. Okay? Tell your neighbor.
Yeah, I don't think that just because the tractor
Yeah, it'll change. Yeah, it starts going on the verticals more,
Yeah.
further over Y, over the X. We're going up.
Yeah, vertical position, yeah.
Correct answer is?
A.
There we go with A. Okay, not as a function of time, but of position. Okay? Good? It's just mg y. Okay? Linear graph. Tell your neighbor.
you'll have more.
No, you- Sorry, I was thinking about the x squared a little too hard. I'm like, just square root this.
What are you doing?
I'm cooking it up, I'm cooking this.
What are you doing?
Well, I mean, that would be a negative x squared. So that'd be another root function, yes, but.
Correct answer is C. Okay, 1/2 kx squared.
Yeah.
Okay, we just made 0 at this point, so we're compressing it. This is just means we're being compressed to the left of our equilibrium point. Okay? How about as it's released, going from negative D to 0? Hopefully, we're seeing the pattern that it is still C. It's as a function of position, not as a function of time. Okay, so I want you to try the same. We've got a frictionless spring launcher, so while it's in here, it's frictionless. That has, we're starting with a compressed length x. How far does it travel along before coming to rest? Because of friction. So first draw potential energy. That is step 1. Draw potential energy. How did we do? Like some kind of parabolic, yes. You're starting in compressed mode. Parabolic. Yes. And step 2, find where kinetic energy is 0. Yep, good call. Find where kinetic energy is 0, and then figure out your mechanical energy. That is step 2. Step 3 is graphing mechanical energy based upon what you know if it's conserved or not.
But you need to do mechanical before you do kinetic.
You do. Sorry, did I say kinetic? Do mechanical, figure out mechanical energy based upon if mechanical energy is conserved or not. Okay, from here to here is in a straight line. Yeah. How do we know?
It's frictionless.
Because it's friction, and friction is going to be constant. coefficient times normal force. Neither of those are changing. Okay with that? So it goes from here to there as a straight line. That was not too bad. You are correct, but it's close.
I didn't trust her.
Okay? Final step, graph kinetic energy. I'll start easy. How does it get to this elevated position? Is it A, B, C? Have a conversation.
Mr. Powell, you got a shirt.
It's A.
Oh, yeah.
Because I'm back. So the fashion looks like now, but I'll be better at it.
I wish it would next.
What do you say, A, B, or C?
A.
A is correct. Okay. You have to add up, stack up to get the red line. Good with that? Okay. How would this be modified if there was friction in the launcher? It has the same friction along the track, like everything. That makes sense? Have a conversation, brainstorm what's gonna look like.
That mechanical energy is going to be decreasing at the solid, the same.
Yeah, so it's just decreasing.
Just make A go up to
It
the.
wouldn't be at the same rate though, as
It-
it is.
You have the same.
He said with, it's with friction, the same friction.
So just look like
Okay, yeah, so then it would be the same.
Yeah,
Yeah.
and then everything else would be the same. Well, maybe actually the kinetic energy wouldn't be
You'd have to move.
down. Okay, we know the potential energy of the spring would stay the same.
Well, your potential energy of the spring would have to go up, right?
Well, it wouldn't have to
Or it
go
would have
up
to start high.
to have the same mechanical energy.
Yeah, because you have to add up stuff,
Did
right?
it say it's going to the same spot?
No, the only thing that's forgiven is that for friction, so.
Yeah, I was gonna say, so.
Oh, wait, so you just like move the, shift the whole mechanical energy, right?
Yeah, straight slope. So if we start with again.
It's not all of them,
Same
but it's always
like the spring, same things for kinetic energy are different except for
So you have to move your mechanical energy.
mechanical energy is never conserved, which is fun.
Well, this is gonna be a weird looking kinetic energy
And then
graph.
are you looking at this curve, is the mechanical energy change?
Okay,
Oh, I don't like that graph.
ready?
Yeah.
With friction, we'll stop sooner.
Oh, yeah.
But what we're gonna do is we're gonna keep the same slope of that. Because friction hasn't changed, the value of friction hasn't changed, so I'm gonna just do this. Trying to keep it parallel. Okay?
Those are
You
pretty
start
parallel.
pretty parallel.
Yeah. You know,
Pretty parallel.
it starts and how it ends.
That's how you can't compare it.
That was provably.
Okay, right, now you can't compare it, but So mechanical energy is decreasing the entire time, okay? Kinetic energy, so did we change potential energy? No, we're still compressing about the same, it's based upon the position, not really the scenario per se. Okay? So your kinetic energy is gonna end up here. It's gonna do something wacky like that. And then carry it on down.
That's what I,
That's me.
Okay.
Damn, Sir Isaac.
So was mechanical energy conserved before the like during the, right? Is that graph of mechanical energy like after the period of during which mechanical energy is conserved, or is that over the whole?
That's over the whole thing,
So
because we have friction in the launcher now.
So the previous graph was like,
Previous graph was without friction in the launcher. This is with friction in the launcher.
lines? I hope not, like straight lines.
Good?
They have a constant slope.
Yeah?
Yo, eyes, that they're never in actual.
We actually got.
Alright. Potential energy graphs. Alright, so, this is a popular type of question, so we're just graphing potential energy, not just categories of energy. It's like, this is specifically set up for potential energy, so we'll do a U versus position, U versus X, okay? The slope of this line, tangent line, is not equal to the force, but the negative slope, not the inverse, just the negative. Okay, we're not making a perpendicular line to that. Okay, so you have the tangent line, and then you make that slope negative, that's equal to the force.
So if the slope was 2x, it would be negative 2x, and that would equal the force.
Correct. Okay, good with that? Watch that. There's a positive value and a negative value with your multiple choice in those. Stinks. Okay. So if you're given the net conservative force, that's equal to the integral under that, area under that, the integral of that is equal to the negative change in potential energy. But this is very popular. So, kind of hit this quite a bit. I feel like we're good with that. Are we good with that? Like, I want you to think through that yourself. I'll just blast through it. We talked about it last week. That, okay, the direction of the conservative force has a positive slope, so it's downward, constant downward force. Okay, the sign of the work done by the conservative force, positive. Okay, because the work done is equal to the negative change in potential energy.
The work is negative. But the work is negative because it's in the opposite direction of the plane.
Right, we're doing negative work. No, blah. Wait a minute. Being raised up, sorry, I was dropping. It's raising up, so we have, negative work is being done, and we're gaining potential energy. Okay? Going from here to here. Okay? Yeah. Good? Yep. Okay, what about lowered? Okay, so still looks like this. The slope of this, still a positive slope, so force of gravity is the negative value of that, so downward, okay? The sign of work done is we're doing positive work because we started here and we're decreasing the potential energy. Okay, that's the wacky part. Okay, you're not going backwards in time, you're just getting lower. Okay, the slope is still positive. When we do slope, don't get confused by the which way you're reading the graph. The slope is just like math class. That's a positive slope, just per definition. Okay, does that make sense? So you're reading, for this case, you're reading backwards. So in this case, it's doing positive work and you're decreasing potential energy. Okay, because you've got a force going in the negative direction and you are moving, your displacement is also negative.
The force is negative.
Force is negative. Negative because you have a positive slope, so the force is in a negative direction. Good? Okay, try to run through this.
This is a.
Okay, so your graph looks like this. Yes? Similar, yeah. Parabolic. Okay. The direction of the conservative force. Okay, at this point, you have a negative slope. Let's I'm gonna match this with a picture here. At this point, you've got a equilibrium position. Okay, as we're going this way, the force is going which way? In the positive. So we have a negative displacement, so we're over here. For the slope of this is negative, so you have a positive directed force. As the spring's been stretched past the equilibrium point, you have a positive slope, so you have a negative force. So you go this way, the force is going that way. Okay. The sign of work. So if we're going this way, we have a negative displacement. The force is in the positive direction. You have negative slope, positive force. The spring's doing negative work, and we're increasing potential energy. As it comes back this way, displacement is positive. And the force is also positive. So it's doing positive work. We're decreasing potential energy. As it goes over here, you have negative force, so positive slope, negative force, positive displacement, you have negative work done by the spring, you're increasing potential energy. As it comes back, you have a negative force, because you have a positive slope, so negative force, you have negative displacement, so you have positive work, and we're decreasing potential energy. Woo! Hold on. We seeing, how to like digest this. It all comes together. Okay?
And just the conservative forces and conservative one.
This is just conservative forces. Okay? Oh, what am I doing to this? Oh, I think I know what I'm doing to you. Okay.
Oh, gosh.
I don't know why I put this here.
Oh, I just want 2067 weeks, please.
Hold on.
So we're actually doing Calc 3, vector calculus.
And we're jumping right in.
This is an odd spot to have
It
this.
is an odd
Yeah.
spot to have
This just like came out of nowhere.
Was that integrals are melting your mind? Good. Calculus 3.
That
makes sense. That's wrong.
It just is folding all sorts of
Hey,
stuff.
that's a 3-4-5
I
triangle
slept in
though.
like 15 minutes almost later because I couldn't.
Alright, well,
I got up and I was
This
just
is fun. I like this.
Whoa,
like, the whole time I was just
whoa. I don't know why I did that. We're gonna jump to something, we're gonna run with the theme here. Alright, we'll come back to it in case we're running out of time, we'll come back to that. Okay. Tell your neighbor and tell them why you think so.
So,
Only conservative forces would be words, mechanical energy is conserved.
right, so if mechanical energy is conserved and the potential energy goes
Right.
negative, that must be one kinetic energy is better change to that energy to be zero. That means that x equals b is the highest.
You went with the graph.
You did something weird. But I think
Actually
actually
went up and then into the
Yeah,
graph.
that made sense there.
Oh, wait.
I'm flip-flopping this.
Yeah, yeah, it fell off the table, which means that down here, and then it did something.
Ripped off my
The spring, the spring is down
I
here.
thought about
You jump
it.
into the spring back down.
Your spring is negatively compressed.
Yeah. Actually, no, because that.
Yay. Correct answer is?
B.
So confident.
Confidently. I agree with you. You agree with me? That's good.
Okay, here we go, ready?
Yeah.
We know it starts at rest at this location,
So,
I'm immediately not confident.
right? At this point, our kinetic energy is 0. So our mechanical energy is here. Is everybody good?
Oh,
Mechanical energy is conserved. So this is now the ceiling. For this scenario, this is what happens. Based because they told us right here. Starts at rest. Initially,
It's initially at x equals d. No, we just know it starts at x equals d.
no clue if it's at rest.
yeah, let's say at rest.
Yay!
Okay? Your potential energy during this time is going to look like, see how I'm doing that? Like that's 0. It's gonna look like that. Does that make sense? It is legal for potential energy to be negative. It is illegal for kinetic energy to be negative. Because what part of that is going to be negative? Okay? Does that make sense?
No hesitation.
Your x is simply just a reference point.
So green is KE, right?
Correct.
How can KE be higher than max input?
So this plus, like, this negative value plus this red value, no, plus this green value has to be the red value.
If you go further than A, how does it have more potential energy than?
It doesn't. This is just the function. So, it's a great question. I'm gonna table that momentarily, Antonio. Okay. So, does everybody see what we're doing here? Okay. This is the function that this is doing. Okay. Let's say it wasn't at rest. Let's say it was pushed. What that means is our ceiling is now higher. And I'll do this. Okay? You good with that? I wanted you to wrestle with this. Here's the, like, kind of like giving you the definition of a derivative with limits, and you do all this, and then I'm like, oh, here's this thing called power rule. The hack on this one is pretend this is a marble and it rolls on a track.
Gosh, dang it.
It's gonna be the fastest here,
Oh.
okay? And this thing's gonna, if it started at rest, it's gonna roll. Whoop, whoop, whoop. It's gonna do that. That make sense? Okay?
D. No, actually. I didn't read the question.
Your neighbor. Of the choices you're given, A is the best option.
Yeah.
Does that make sense?
Yep.
You're increasing your potential energy, therefore you're decreasing your kinetic energy.
My marbles go down. Why did you go down? I have an idea. I know this one. I think I know this one too. Yes, damn. Yes.
Tell your neighbor.
D.
What about B?
B? Yeah, look at number 4. Look at D. At X.
Oh, I thought you were holding up a 3. I
No,
was
it's
like,
a
what?
4.
Okay, well, I can't see your pinky.
What, how do you not see my pinky?
What do you mean, how can I not see your pinky?
Correct answer is
D.
slope is 0.
Yeah.
Not like this.
Good?
Somehow we gain mechanical energy.
Say what? Yep, totally can. So, we know that
Because
the
otherwise,
conservative force is equal to the negative slope. Okay? Do what? Yeah, not inverse. Akshay, question?
Is this still the, wait, actually, never mind.
If I removed all the it's still the same data.
Where it bounces back and forth.
Okay,
Oh.
here's stable versus unstable equilibrium. I'm just gonna tell you this. Stable equilibrium is in B. If you put it at rest, it's gonna stay there. There's no chance it's gonna get out of that. Okay? If you put the marble at this point, it's at rest, but it's not stable. It could roll either way. Okay? They use this a lot in chemistry. This is an energy well for electrons bound to an orbital state. In order to jump out, it's got to have a certain amount of like excitation energy, like excited. I don't know.
It gives
What's,
free energy? No.
It gets excited.
it gets excited and is able to jump out over this energy well.
But the other one just has like any amount of.
Right. This is like you can't get closer to the nucleus or something.
So is it?
Or something.
Or something. I don't, we just made this graph up.
So does stable equilibrium only happen at concave flips?
Correct.
Points of inflection?
Yep. The marble's not gonna roll. In order to, it would need some more energy here. It has potential energy and can convert that kinetic super easily. Here, in order to have more mechanical energy, you need to be given that by something outside. Does that make sense? Yeah.
Yes, we do the second semester.
Trying to add.
You can literally think of it as like an energy well.
We're gonna call that.
Yay! Because the idea is that, negative potential. And that one has.
Shut it out and answer it, right?
Did you get that?
Look,